We're now going to go to something just a little bit more complex, and instead of ethane, we're going to look at butane. And I do recommend, it's probably going to be easiest if you print out or save this slide in the handout and fill it in as you go. So what we're going to do is start with this structure right here, this conformation of butane, and we're going to take it through 60-degree rotations of the front carbon. So the back carbon we're leaving in place in every case. So we're going to start by just converting this 3D structure into the first Newman projection. And what we're doing is we're viewing from left to right, viewing like this, such that here's your front carbon, here's your back carbon. And you can see that on the front carbon, we have a methyl group going straight down, that's this methyl. On the back carbon, we have a methyl straight up. And as a reference point, I put a gray circle around that. So there's the methyl on the back carbon. So what we're going to do is start here and do a 60-degree bond rotation and see what we get. Now, in terms of energy, in this first conformation, this is basically as good as it gets because your biggest groups, the methyl groups, they are as far apart as you can get them. The conformation is staggered, so this is called the staggered anti-conformation because your big methyl groups are anti. Because this is our lowest energy conformation, we're going to say the relative energy of this one is 0. And the dihedral angle that we're going to measure in each of these is between the two methyl groups. So in this case, the two methyls are 180 degrees apart. So let's look at this and see what happens when we rotate the front carbon 60 degrees. So basically what we're doing is we're going to rotate in every case just clockwise. So I'm going to rotate this carbon to here, this hydrogen to here, this hydrogen to here in that rotation. All right, when we do that, we get this new conformation. So you can see we left everything in the back the same, but now this hydrogen got rotated so it's eclipsing this one. The methyl was moved to here 60 degrees, so it's eclipsing this hydrogen, and then this hydrogen is eclipsing this methyl group. Let's look at this in our molecular model to make sure we can follow along. So here we're going to take this structure, and you can see that in relationship to the starting structure we have, here's this methyl, and then the other methyl I put as a gray atom. And if we look at the Newman projection, right, I'm going to turn it right like this so we can view it in this form, and you can see that here's the bottom methyl group right there. Here's the top methyl group on the back carbon right there. And the bond rotation I'm doing to get from this structure to this structure, I'm rotating the front carbon 60 degrees. So that rotates this like that. So now we go from the staggered to the eclipsed conformation. So I'm going to trust you to follow along using your molecular model. I probably won't show you any more examples with my models, but you can follow along as we do these bond rotations and make sure the structures match. So now, once we get this new structure here, we can calculate the energy. And I've given you a table of conformational energies up here. And we're going to see some different things and talk about them, including a methyl-methyl Gauss, which we haven't encountered yet. We have a hydrogen-hydrogen eclipse, hydrogen-methyl eclipse, and methyl-methyl eclipse. So if we look at this structure, it's an eclipsed structure. Then if we look at what we have eclipsing, we have a hydrogen-hydrogen eclipse, which is 1.0 kcals per mole. We have a hydrogen methyl eclipse, which is 1.4 kcals per mole, and another hydrogen methyl eclipse, which is 1.4 kcals per mole. If you add those energies up, we get 3.8. That's the relative energy of this conformation. The dihedral angle between the methyls, we've moved this front methyl 60 degrees closer to the back methyl. So we've gone from 180 degrees apart to 120 degrees apart. Now we're going to do another 60-degree rotation of the front carbon. So rotate that 60 degrees clockwise, and we end up with a new conformation, this one right here. In this case, we're back to a staggered conformation. But what we end up with are these two large methyl groups still kind of close together, and the hydrogens on one are going to bump into the hydrogens on the other, so that is considered a gauche. And you see up here in our table, the methyl-methyl gauche is 0.9 kcals per mole, so it does raise the energy of the system. But that's our only high energy interaction in this particular conformation. So the relative energy of this is just 0.9. The dihedral angle between the two methyl groups here is 60 degrees. Okay, next we're going to do another 60-degree rotation of the front carbon. And when we do, we end up with another eclipsed conformation. So hopefully you're starting to see the pattern. With every 60 degrees, we go from staggered to eclipsed, to staggered to eclipsed. From here, let's calculate the relative energy of this conformation. We have a hydrogen-hydrogen eclipse, which is 1.0 kilocalories per mole. We have another hydrogen-hydrogen eclipse, which is another 1.0 kilocalories per mole. And we have a methyl-methyl eclipse. Here we're putting two large groups directly in front of one another. That's a very high energy interaction. It raises the energy by 2.6 kcals per mole. So add that up. The relative energy of this conformation is 4.6 kilocalories per mole. Now the dihedral angle between the two methyl groups is 0 degrees. Okay, we're going to rotate another 60 degrees. When we do that, we get another staggered conformation. But you see these two methyls are 60 degrees apart. That is a methyl-methyl gauche. So we call that a staggered gauche conformation. That's our only high energy interaction here, which is 0.9 kcals per mole. And the dihedral angle between the two methyl groups is 60 degrees. All right, continuing on, do another 60-degree rotation of the front carbon in a clockwise direction. When we do that, we end up with an eclipsed conformation. With this one, let's look at our eclipsed interactions. We have a hydrogen-methyl eclipse, which is 1.4 kcals. Another hydrogen-methyl eclipse, which is 1.4. A hydrogen-hydrogen eclipse, which is 1.0. The relative energy of this is 3.8 kilocalories per mole. The dihedral angle between the methyls is 120 degrees. And finally, if you do one more 60-degree rotation, you've come an entire 360 degrees, so you're back where you started. Let's take a look at this and find our extremes. So for our energy, we have one conformation with a relative energy of 0 right here. That is our lowest energy conformation. Then as you go through and look at the relative energies, you find one that has the high extreme, 4.6 kcals per mole. This is our highest energy conformation.